Okay, so in this lecture, we will consider a concrete process and write a realistic block diagram for a feedback control setup. Last time we had a simplified feedback control loop that we analyzed and we derived the closed loop transfer function. So now we will add more details to that and make it more realistic. And then for your homework, I will have you solve for the closed loop transfer functions. So here's the process set up. What we have is liquid flowing into the tank. And there's a mixer that keeps it well mixed. And then the liquid flows out of the tank, but at a different temperature than what it was coming in. So this is the input temperature, and this is the output temperature. And the purpose of this process is to heat up this liquid. And to do that, we feed steam through this pipe, and the pipe is fed through the reactor, and it's coiled around to increase the surface area of contact between the surface of the pipe and the liquid. And there's steam flowing on the inside of the pipe, and that keeps the pipe very hot, and then heat transfer occurs from the pipe walls to the fluid in the reactor, and that is what heats it up. So this is a liquid heater. So the goal here is to control the outcoming temperature. So this is the controlled variable. And I guess I can put units on these. So this would be kilograms per minute. This would be degrees C. This would be degrees C. And this would be kilograms per minute. And we're trying to control the temperature in the face of disturbances in the input temperature. So this is the disturbance variable. Input temperature. So this is output. I'll say temperature of the output stream. That's what we're trying to control because the goal is to heat the liquid to a desired temperature. And this is the temperature of the input stream. And since the TI, the input coming temperature, is varying a lot and it's fluctuating, we're going to control the temperature via this control valve. And this is going to be the manipulated variable, which is the flow rate of steam. This is what's manipulated. Flow rate of steam. I didn't leave enough space in there for units, but I'll write them here. The steam flow rate would be kilograms of steam per minute. And you can imagine if the temperature, T, is too high, then what you would do is close the control valve in order to decrease U, our manipulated variable, which is the flow rate of steam. So I'll also write this is the control valve, the control element. Control element, or the control valve. Element is less specific. So let's outfit this with a feedback control scheme. So this is going to be for feedback control. And remember, in feedback control, we would measure the controlled variable. So you can imagine sticking a thermocouple in here. So this is a thermocouple. Let me draw it from here. It's a thermocouple. Or temperature sensor. And it measures the temperature of the liquid. And then the thermocouple is hooked up to a temperature transmitter, which we will abbreviate as TT for temperature transmitter. Oh. So TT stands for temperature transmitter. And the temperature transmitter outputs a milliamp signal. So I'll draw that with dashed lines. And so this is the measured temperature, Tm right here, right? And this has units of degrees C. So we're thinking of Tm, which is the measured temperature. And it's not exactly the same as T temperature because there could be a delay between the sensor reading what the temperature is owing to the time it takes for heat transfer. So this is the measured temperature, but then the temperature transmitter converts that into an electrical signal, a milliamp signal, and we usually decorate those with a tilde. So this is units milliamps. And this milliamp signal is sent to the temperature controller. So this is our feedback controller here, TC. So TC is our temperature controller. And we also feed to our temperature controller a set point for the temperature. So this would be the set point. And I'll decorate that with a milliamp, with a tilde too, because this is going to be a milliamp signal sent to the controller by the computer. So, and then the temperature controller, the idea is the controller decides what to do with the manipulated variable, but now what the temperature controller actually does is outputs an electrical signal. So I'll draw this with dashed lines again. And we'll call it P tilde, milliamp for electrical signal. And this electrical signal is fed to a current to pressure transducer. And so that's denoted as I/P because I is used for current. So I/P, current to pressure transducer. So it takes as input a current, a milliamp signal, and it spits out a pneumatic signal. Okay? So let me move all of this up because I barely have enough room. Okay, so it outputs a pneumatic signal. Pneumatic means air, associated with air or gas. Could be nitrogen, or it could be air. So I'm decorating with this hash here. So this is P. This is an actual pressure, milliamp. And that's what the current to pressure transducer does. It converts an electrical signal into a pressure. And that pneumatic signal pushes down on a diaphragm on the control valve and adjusts U. And we'll talk about control valves later. And so I should also denote this is not any ordinary control valve. This is a pneumatic control valve. So it's actuated by a pneumatic signal. And I will uncover later how these work. That will be the next lecture. So that's the current to pressure transducer, right? And you'll notice, so I did use different style lines for the flow of information here. And I'll just write down these for reference. So this is used for process piping. And here, it's this one here is sort of conceptual. It's a wire that is hooked up to the sensor. This is a pneumatic signal. So air or gas pressure. And the industry standard is that this signal will vary from 3 to 15 psi. And usually I would ask in class a question, why would they choose 3 psi, why not 0? And the answer is because if it's 3 psi, you can distinguish between the minimal output of the controller, of the current to pressure transducer, so the minimal output, and the loss of air. Because if there's a hole in your air line, then you'll lose air and it will read 0 psi, and then you'll know something's wrong, you're losing air. So this is for troubleshooting. And then the dashed line is an electrical signal. And here again, there's an industry standard. And it doesn't start at 0 because that would be a loss of electricity, right? Or a wire has been cut. And the industry standard is 4 to 20 milliamps. Okay, so that's a unit of current. Okay, so to reiterate, we have our thermocouple and the measured temperature of the water that's fed to a temperature transmitter, which outputs a milliamp signal, which is fed to the controller. That measurement in milliamp signal form, in electrical form, is compared to the set point in electrical form. And based on the error, the controller spits out a value for the pressure, but it's in the format of a electrical signal. But then the current to pressure transducer converts that electrical signal into an actual pressure, which then adjusts the flow rate U, okay? So this is a more realistic control system that includes many different compartments. And so now what I would like to do is write a block diagram for this. And so the block diagram will be a bit big, so I'll reduce the size of my pen. Okay, so way on the left, what we start with is feeding in the set point, okay? So I'll start here. So this is T set point. And let's let this actually be the set point in degrees C, right? So this is what you might type in on a computer. And then this is called the measurement gain, and it converts the set point in degrees C into the milliamp signal. So it's really just a scaling factor. And this is what is actually fed to the comparator that computes the error. So this is the set point. And so I'll decorate that with a tilde, right? So that's this up here. That's this right here. That's your T tilde set point in milliamp units. And we'll actually compute a gain, Km, in the next lecture to demystify what this gain is. But it's just a scaling factor, okay? And then this is what is fed to your comparator, which computes the error. Okay, so we have a plus here because the error is defined as a set point minus the measurement. And so eventually we'll feed the measurement in the bottom. Okay, so this is going to output the error, which is the error signal, E. And the error is actually in units of milliamps. So in practice, that's how a controller works. It computes the error in milliamps. Okay, so this, I'll use a color here. Let me use a different color since we used yellow up there. Okay, so this is here is the error signal. And this here is called the internal set point because it's internal to the controller. It's in milliamps and not in the actual units of the controlled variable. So then this error signal is fed to your feedback controller. And the control law is represented by a transfer function GC of S. So this is our feedback controller, okay? So I'll call this FB for feedback controller. And that's your control law GC of S. And then last time we extracted the controller as directly outputting the manipulated variable U, but here we're including more details. So what the controller really does is outputs a milliamp signal, P tilde, to the current to pressure transducer. So the controller doesn't spit out a pneumatic signal, it spits out an electrical signal, okay? It's a computer, right? So it can't spit out an electrical signal. And then we have our current to pressure transducer, and that's often modeled as a pure gain, so there are no dynamics associated with that, Ki/P. It's just a number, it's just a gain scaling factor, and that converts this milliamp signal into an actual pressure that should be put on the control valve. So this is an actual pressure. This will be PSI. So this is your I to P transducer. And then that pressure, I should put a star on here because these are in deviation form. So that pressure is then fed to your control valve. And interestingly, control valves often have dynamics. They don't respond immediately. usually we can neglect them, but I'll keep the dynamics here just in case. So this is basically, so it's not just a gain. So this is how the control valve responds to a certain pressure and how that changes the flow rate. And that can often be quite complicated, but usually this is just a pure gain and it's a scaling factor. So this is finally the manipulated variable, the steam flow rate. So this is our control valve. So V stands for valve. Let's see, V. This is our control valve. So C here stands for controller. Yep, so this IP right there. And finally, we have our manipulated variable. So this is our manipulated variable right here. So that's our manipulated variable, which is the flow rate of steam. So the steam could be through a jacket surrounding the reactor, or it could be in a pipe that's then coiled and in contact with the fluid. So now this steam will affect the temperature of the process, and we use the transfer function G sub U to denote how this variable U, the manipulated variable, affects the controlled variable. Okay? So what this does is it outputs not the temperature quite, but the contribution to the temperature by the manipulated variable. So I'm going to move all this down because I didn't leave enough room for the disturbance variable. Okay, so I'll put it down here. Yeah. Okay. So let me draw with units. So this would be kilograms per minute, the flow rate of steam per minute. And this is your process right here. So this is the process itself. And in more details, this is how U affects T. But U isn't the only thing that affects T, right? We have the disturbance variable that affects T as well, Ti. Okay. So we'll have another sum block here. Oh, here's a sum block. So T is a sum of two contributions, a contribution from the manipulated variable and also a contribution from the disturbance variable, which here is T sub I, which is our disturbance. And then we'll decorate this with G T sub I of S. This encapsulates the dynamics of how Ti affects T. So this is your disturbance variable. So I'll highlight this because that's our disturbance variable. Right? And then finally, that's what T is, T star. That's your controlled variable. Finally, we get what it is. Controlled variable. Controlled variable is still the sum of two contributions, one from the disturbance variable, one from the manipulated variable. The idea is whenever the disturbance upsets the process here, we can take action via the manipulated variable and have this cancel out this, right? So that then T star remains at 0, which is its set point. All right. So the feedback loop, though, is, let me decorate these with the units. This is degree C, and this will be in degree C as well. And in a feedback control scheme, remember, we measure the temperature. So let's measure the temperature right here, right? So this is actually fed to a sensor, right? So this is your sensor. And this has dynamics as well, because it's not an immediate reading necessarily, right? There's heat transfer that needs to occur in order for your sensor to read the temperature. We studied that in CH 361. So this is your temperature sensor. So that's why the S is there. And then the sensor outputs TM. So this is a sort of conceptual thing, just to note that T is not the same as the measured temperature. And this is in degree C. So those are the dynamics of, for example, heat transfer to the sensor. Okay? And then we don't feed this right back to the comparator. First, we need to convert that into a milliamp signal as well. And to be consistent with this over here, we also need to use the same gain here, Km, so that they're comparable. So these Kms have to be consistent. So it's not an accident the Km appears both here and here, right? That's not an accident because in order to compute the error, we need a correspondence between the internal set point and the measured temperature in milliamp form. Okay, so finally what happens is this now is converted to milliamp form. And this right here is Tm tilde. That's your milliamp signal. That's in units of milliamp, okay? Okay, so this here is your temperature transmitter. Because it converts the measured temperature into a milliamp signal to compute the error. And that completes our feedback block diagram for this process. And you can see there are more details that we added because before, all we had were these, right? We had this one, we had the disturbance variable, and we had the controlled variable. So that only those three were included in our simplified block diagram, and now we have many more. And so for your homework, what I would like you to do is derive two different transfer functions. One for the servo. So this is the closed loop. Let me go back to the thick pen. I like that one more. So there are two closed loop transfer functions that we can derive. One of those is associated with the servo response, right? So that's when you change a set point, how does the control variable respond? So that's here the output is T star and the input is T set point star. So this would be the servo response. The other is for disturbance rejection, the regulator response, and that's how T star will respond to a disturbance. And your disturbance here is Ti star. So this is the regulator response. So I'll leave that to you for your homework, but you can use the same logic as before and make sure you go through step by step. Don't try to just look at it and guess, use first principles. And note that whenever I derived the closed loop block diagram from before, I sort of started with a controlled variable, right? And I systematically went through and I went through here, and then I wrote error, and then you sort of systematically connect them until you arrive back at T. And then you will have an implicit function or an implicit equation for T, and you can solve for that. Okay,